Supervised machine learning is an important way to do relation extraction. The algorithm works as follows. We choose some set of relations we'd like to extract. We choose some set of entities we'd like to extract the relationship in between, unless it presumes we have some named entity tagger that can tag those entities. And now we find some data and we label it. So we choose some representative corpus, we run our named entity tagger and label the entities, or we label them by hand if it's small. And now by hand, we label the relationship between each entity. So all the relations we're interested in, we label all of them in the corpus. And now we break our corpus into training, development, and test like we have done in the past for all of our classification tasks. And now we train our classifier on our training set, and then we test it on our development and test sets. For efficiency reasons, we often modify this algorithm slightly. We first find all pairs of named entities, usually occurring in the same sentence or right near each other, and we build one classifier which just makes a yes-no decision. Are these two entities related in some way? And if so, we then run to a second classifier which classifies the relation. So why do we build two classifiers instead of one? Usually, if we have a lot of data, this simple Boolean classifier that says these things are probably related in some way can be run very quickly, can be trained fast and run fast. We can train it on a lot of data. And that will eliminate most pairs because most entities in most sentences are probably not in whatever relation we're looking for. And then we can use distinct feature sets specific to deciding if two things are related to each other at all and deciding if they're in a particular relation. So again, we might use the relations, for example, from the automated content extraction or ACE tasks. Remember, we had 6 meta relations and 17 subtypes of those relations. And given that set of relations, our task is to classify the relation between two entities in a sentence. So imagine this sentence: American Airlines, a unit of AMR, immediately matched the move, spokesman Tim Wagner said. So we have two entities, American Airlines and Tim Wagner. And our task is to decide what the relationship is between those two entities. And it might be family or citizen or employment, or it might be nothing, might be unrelated, or it could be subsidiary or founder or inventor and so on. So what are the features we're going to use for this task? And let's for now imagine that we're doing just the task of deciding what the relationship is between the two. So here's the sentence again. We have two mentions. Mention 1 is American Airlines and mention 2 is Tim Wagner. So one important feature is the head words of the two mentions. So the head word of American Airlines is airline. So we'll talk more about head words when we get to parsing. But in this case, the American Airlines is a kind of airline. And the head word of Tim Wagner will be Wagner. And so airlines and Wagner might be useful features. And we can create a new feature, which is just the two combined together. And sometimes that's going to be useful because we're going to see the two heads together often enough that that feature might actually tell us some information. So we have 3 features so far: airlines, Wagner, and airlines Wagner. We might throw in the bag of words or even a bag of bigrams that are in the mentions themselves. So the word American, the word airlines, the word Tim, and the word Wagner are all words that occur in the two mentions, and the bigram American Airlines and the bigram Tim Wagner occur in the two mentions. And we might pick words or bigrams that are in particular positions to the left and right of the two mentions. So for example, the word before mention 2, so we'll call this word -1 with respect to mention 2, is the word spokesman. And the word after mention 2, so we'll call this the word +1 with respect to mention 2, is the word said. Or after mention 1, if we're counting punctuation, our first word there is a comma. If we're not counting punctuation, our first word is a. And the word before American Airlines is nil. There's no word before American Airlines. So we can have these words that are specific at specific positions before and after each mention. And we can have the words that are in between the two mentions. So for example, this between region, so a unit of AMR immediately matched the move spokesman between American Airlines and Tim Wagner. We can throw in a bag of those words. So AMR, of, immediately, and all this sort of thing. Or, in fact, if we have enough compute power, we can throw in bags of bigrams as well. So all pairs of words between the two entities. We've already said that named entity type, very important for relation extraction. So I want to know that the first entity is an organization. So American Airlines, an organization. The second mention, Tim Wagner, is a person. And I might create a new feature just by concatenating those two together. So a new feature called org person, which is the concatenation of the two named entity types, or a feature whose value is org person. And then we might add what's called the entity level of the two mentions. So the entity level is whether an entity is a name, a nominal, or a pronoun. And very often what we have is names, but we also get nominals and pronouns acting as named entities. So these two are both names. So American Airlines is a name and Tim Wagner is a name. But if they were instead it or he, then we would call this a pronoun. And if it was a nominal like the company, so not a proper noun, then we would call that nominal. So again, another feature we can use for each of the two mentions. And then we haven't talked yet about parsing, but we can use lots of features related to the parse. Once we parse the sentence, we can extract lots of useful parse features. And just to give you the intuition without going into the details of parsing, we could extract what's called a syntactic chunk sequence or a base chunk sequence. So there's a couple of noun phrases followed by a preposition phrase. So here we have a noun phrase and a noun phrase and a preposition phrase and a verb phrase and a noun phrase and so on. So this sequence of syntactic chunks, we can actually run a parser and then flatten out the parse into what's called a constituent pass, and we'll talk about how these work later, but basically this is saying that we see the parse has a noun phrase whose parent is a noun phrase, whose parent is a sentence, whose parent is another sentence, and so on. So it's a way of taking a complex parse tree and flattening it out. And we can have a dependency path. For example, we can say that the head said has an argument which is Wagner, and an argument which is matched, and matched has an argument which is airlines, and so on. So any of these kind of things can be used as parse features for relation extraction. And finally, we can use gazetteer and trigger word features. So a trigger word is just a list of terms that might be useful in this particular domain. So for example, kinship terms are obviously useful for deciding if we have the family relation. So a word like parent or wife or husband or grandparent are obviously words that are going to help in finding a family relation. And we can get these from online databases like the Wordnet Thesaurus or other places. And a gazetteer feature is a list of useful geographical or geopolitical words. So we might have a country name list in a gazetteer, or other kinds of subentities like names of rivers or lakes or states or cities and so on. That's going to help us know that San Francisco is in California and California is in the United States and so on. And we often, when we talk about gazetteer features, we might, for example, for detecting named entities like person names, having a country name list isn't as useful, but having a list of common person names in whatever language we're working in might be a very useful feature. And so we often call those gazetteer features, even though a name list isn't really a gazetteer, it's a list of names. But sometimes we use the word gazetteer to mean to any long list of useful proper nouns that might help us in doing named entity extraction. So in summary, for our sentence, American Airlines, a unit of AMR, immediately matched the move, spokesman Tim Wagner said, we might have a whole series of features. So we might have the entity type of the first mention being org, and of the second one being person, and the head of the first one being airlines, and the head of the second one being Wagner, and this concatenated type feature whose value is org pers. And then the bag of words of all of the words between the two entities, and the word before entity one, which there isn't one, so that'll be none or nil, and the word after entity two, which is said, and then all the various parse features that we talked about. And we combine all these features, and we extract them from our training set, we extract them from our test set, and we do standard classification. And of course, you can use any classifier you like. We've talked about the maxent classifier and the naive Bayes classifier. There's other classifiers like SVMs and whatever you like. And in each case, you train your classifier in the training set, you extract all these features for deciding a relation, train that classifier in the training set, and then you tune any of your hyperparameters on the dev set, and then test on your unseen test set. Like other kinds of classification, supervised relation extraction is evaluated with precision recall and F1. So just as we saw with other kinds of classification, the precision is the number of correctly extracted relations over the total number of relations extracted. And the recall is the number of correctly extracted relations over the total number of true gold relations. So we're going to need a test set that's hand labeled for the correct relations so we can compute the precision and recall. And again, the balance, the F1, is 2PR over P plus R. So in summary, supervised relation extraction lets us get high accuracies if we have enough hand labeled data and if the test set is in the same domain as the training set. The minuses of supervised relation extraction are the expense of labeling a large training set and the general problem with supervised models, which is that they don't generalize well to different genres. So if we know that we're going to run our system on a similar genre to what we have in training, then supervised is a good approach. If we're worried that the test set's going to be very different than the training set and we have to be able to be very robust to different genres, then we're probably going to need to turn to unsupervised or semi-supervised methods. So supervised relation extraction, an important way to do relation extraction in cases where we can afford to label a training set and we think our test domain is going to be very similar to that training domain.